All right, in this video, we are going to be covering sections 1.7 and 1.8. This is all about inequalities and absolute values. That's what we're going to work on during this video. So this will actually be one of our shorter videos that we do, so good thing there, so a little bit easier for y'all students today. So let's begin section 1.7, which is titled Linear Inequalities. So a lot of stuff here. You don't really need to copy all of this down. This chart is posted on Canvas already under the blank notes that I've put, but I do want to run through a few things here just so we can talk about what we're going to be looking at. So we solve inequalities the exact same way that we solve equations. Your goal is to isolate the variable, whatever it may be, to one side of the inequality. But the difference is that solutions can be written in three different ways. So the ways that we're going to look at this is first, and I'm going to go from left to right here, we're going to look at interval notation. Interval notation is the most popular notation that we're going to use today, but I'm actually going to come back and talk more about this in a minute once I go over a few other things. Set builder notation. This is usually when you solve an inequality, this is usually the first notation that you're going to get. Because what you're going to realize is that you are going to get, there's a bunch of them here, you're going to end up solving an inequality and one of these is going to pop up. So I'm trying to underline all of them here really quick. Depending on what happens there, that is what dictates how you answer the other two parts. Now you'll see that there's a combination. If you look at the first four, those are what we call compound inequalities because you have a number on the left, which is A, and a number on the right, which is B. Now those inequalities can either not have the equal sign, which is the line below the inequality. It can have the equal signs, or it can be a combination where one's an equal and one's a not, and vice versa. What we're going to see as well is singular inequalities, which are the second four that I've underlined, where you either have x is greater than a number or x is less than a number, or maybe there's an equal sign on it, whatever it may be. Once you have that, which is what they call set builder notation, one thing you can do is you can turn it into a graph. So you can take whatever that inequality is and you can display it on the graph to the right. So you see that, for example, on the first one, you have A is less than X is less than B. Well, I plotted A and B on the graph. I'm going to use parentheses. So anytime there's not an equal sign, you use parentheses, and then you shade in the part that it's talking about. Since X is between them, we shade in the middle part. The only difference is that if you do see an equal sign on them, make sure that you use brackets, and we're going to talk more about that. So that's the parentheses and brackets part right here. Parentheses correspond to inequalities that don't have an equal sign, and brackets correspond to inequalities that do not have equal sign, or sorry, that do have equal sign. Sorry, misspoke there. If you jump down to the bottom four, when you only have one parameter, such as x is greater than a, you would plot a on your number line and you would shade everything in the direction it's talking about. So greater than a would be to the right. If it was less than, as you can see on the last two, it's shaded to the left. Once again, no equal sign means parentheses, equal sign means bracket. Now, occasionally on your homework, I'm going to always do brackets and parentheses, but occasionally on your homework, they may want you to use circles. Don't sweat too much on this. Essentially, parentheses and open circles are the same thing to me, and brackets and closed circles are the same thing. I just don't want you to be confused if you see circles on your homework or your quiz. It means the same thing. I just prefer to use the parentheses and brackets, but that's completely up to you. Now back to what I was talking about. The one good thing about this graph notation is that once you get the graph notation down, it's very easy to represent that as interval notation. You can literally just take exactly what you see. So if it was A to B with parentheses, you would write it as A to B with parentheses. Or you could use brackets, or it could be a combination. Now, if you only have one parameter, that means you're going to have some kind of infinity involved. If you're doing greater than, A is your lower bound, and then if you go to the right forever, eventually you'll get to infinity, versus if you have, let's say, a B value and you want to be less than that, you will eventually go to negative infinity. One thing to note about these is that the infinities and negative infinities always get parentheses because they are not an actual number you can count to. You cannot include them, so you can never equal infinity. So make sure you always use parentheses on that. So that was a lot of talking. I do agree, but it's a lot of information, but the problems actually don't take very long, and you'll see that as we go through and do a bunch of examples here. So here we go. So first one, can you solve this inequality, graph the solution set on a number line, and then express your answer in set builder notation? So when you see a problem like this, kind of like when you did equations, or we did equations a few videos ago, try to get your y's on one side and then see what you have. So first thing I'm going to do is on the left-hand side, I'm going to multiply through by 2, which is 2y plus 2 plus 3 is less than, and then I'm going to multiply the 5 through, which is 5y minus 10. Combine the numbers on the left, and you'll get 2y plus 5 is less than 5y minus 10. You can move the y's to whatever side you want to, but to kind of keep it similar to what we've done in the past is I'm going to move my variables to the left by subtracting 5y, and I'm going to move my constants to the right, which is subtracting 5. This will also give me a chance to show you one other neat thing that you have to be careful about. This will give you negative 3y is less than negative 15. And here is the kicker. Any time that you have to divide by a negative number, and this only applies to negatives as we are seeing here, you must flip-flop your inequality. So in this case, I have to say that now y is greater than negative 15 over negative 3, which is 5. This is your set builder notation. That's all you have to do. But if you want to express this, in a number line or graph notation, I'm going to take the 5. You can plot it wherever you want to on your graph. I want everything greater than 5, which is everything in this direction to the right. And since there's not an equal sign, I have to use a parentheses to express my graph. But solving is no different than what we did back earlier in chapter 1. The difference is if you divide by a negative number on inequalities, you must flip-flop the inequality. We'll probably see that again here in a few minutes. Just be ready for it. All right, number 2. Graph the solution on a number line again, but this time I want you to express your answer in interval notation. So we have 4n minus 1 over 3. It needs to be less than 3 minus n. The part that I do not like is that 3 on the bottom. So to get rid of that 3, I'm going to multiply everything by 3. Now that's not a negative number, so we're good. So we can leave everything the same. Multiplying the fraction by 3, the whole point of that is to get rid of the fraction. So that's 4n minus 1 is less than 3 times 3 is 9. 3 times negative n is negative 3n. I'm going to move my variable n's to the left-hand side by adding 3n. I'm going to move my constants to the right by adding 1, and you should end up with 7n is less than 10. This time there's no negative number, so when you divide by the 7, it doesn't change anything. You just end up with n is less than 10/7. Now they're not asking for set builder notation. The first thing they ask for is the graphing notation. So I'm going to plot the 10/7 wherever you want to. If I want everything less than that, that's going to be to the left. And since there's not an equal sign, I need to use a parentheses. So that is my graph notation. But the good thing about graph notation is that it's very easy to convert this into interval notation. Look at this and tell me if you're shading to the left, what's the smallest number you can have? Well, that would be negative infinity. The number which is the highest here is going to have to be 10/7. The 10/7 you can see from the graph already has a parentheses because there's no equal sign, and you're not allowed to put anything other than a parentheses on the infinity. So your interval notation would be from negative infinity to 10/7. And that is your graph notation and your interval notation. Very good. All right. Now we're going to move into a couple that have what we call compound inequalities. This is where you have the a and the b on each side. That way you're not going to have any infinities. So example number 3, as I want to talk through, is something like negative 2 is less than or equal to 2x minus 5 is less than or equal to 2. In compound inequalities, the difference is that you want to get the x by itself in the middle instead of on one side. So what I want to do is I want to get rid of this negative 5 by adding 5, but in a compound inequality, you have to add 5 to all 3 parts. It cancels in the middle. Negative 2 plus 5 is 3, which is less than or equal to 2x, which is less than or equal to 2 plus 5 is 7. And then if I divide everything by 2, it cancels in the middle, but you notice that nothing simplifies on the outside, so that's fine. So 3 halves is less than or equal to x, which is less than or equal to 7 halves. And if you look at the instructions, they're only asking for the interval notation. The good thing about compound inequalities is that you can easily see your upper and lower bound. The 3 halves is the lowest number, and the 7 halves is the largest number. Since they both have equal signs, we are going to put brackets on both endpoints, and that is the interval notation of your answer. Now, compound inequalities can also be written in a second way. This one's a little bit trickier, so let's do this together. What if it says something like 2x minus 3 is less than or equal to 5, and 5x plus 1 is greater than 6? If they are not put together, don't try to put them together. That's going to cause problems. Solve them separately, and then I'll show you what you have to do. On the first one, if I add 3 to both sides, I get 2x is less than or equal to 8. And if I divide both sides by 2, I see x is less than or equal to 4. On the second one, if I subtract 1 from both sides, I can see that 5x is greater than 5. And then dividing both sides by 5, x is greater than 1. So the key word here is this and. And even though it's not asking for the graphing notation, I'm actually going to think it's easier to visualize this if I draw a quick sketch. So look at the two numbers you have, 1 and 4. Plot both of those on your number line. So 1 and 4. What does the first one say? The first one says is that x needs to be less than or equal to 4. So this says that, it says that we're going to start at 4 and we're going to go to the left. But the x is greater than 1 says I need to start at the 1 and go to the right. This and statement tells us that both lines have to cross, and that part is your solution. So if you look, they cross here at the 1 and they cross here at the 4. So I know that my lower bound is going to end up being 1 and my upper bound is going to end up equaling 4. Now, if you look back at the inequalities you solved, the 1 did not have an equal sign, so we're going to use a parentheses, while the 4 did have an equal sign, so we're going to use a bracket. So there's an example where a compound inequality has two separate different endpoints. Very good. All right, then we get to the dreaded or. So while or means something different than and, so we'll get to the or in a second, but let's work this problem out. Solve this compound inequality, and then once again answer in interval notation, where it says 3x plus 1 is greater than 7, or 3x minus 4x is less than 15. So once again, don't worry about the or right now. We'll come back to that. Solve each one separately. Number 1, subtract 1 from both sides, and you'll get 3x is greater than 6. Divide both sides by 3, and x is greater than 2. On the second one, if I subtract the 3 over, you'll get negative 4x is less than 12. And then once again, be careful. If you divide both sides by negative 4, you have to change your inequality. So it becomes x is greater than 12 divided by negative 4 is negative 3. Once again, with these type of compound inequalities, even with an or, let's draw what we have. So I see that we have a negative 3 and we have a 2. Please make sure you put them in order, not the order you solve them, but the order they actually go in. Read each statement, and I'm going to use different colors this time other than the number line. So x is greater than 2. That means that's this direction. X is greater than negative 3. Well, that actually means you start here and you keep going. And these two lines actually cross. Now the difference is that the word or does not mean they have to intersect. The word or means you have to include both no matter what. So if you look, x is greater than 2 took care of everything in this direction. X is greater than negative 3 took care of everything in this direction. So the 2 has nothing to do with this problem. We're not even going to use the 2. Instead, we're going to use the negative 3, and since there's not an equal sign, we're going to use a parentheses on that, and when you express that in interval notation, negative 3 is your lower bound, and since you go to the right forever, you get infinity. That is your final answer. So, and they have to cross, or you have to include both no matter what. All right, like I said, short section. So that ends section 1.7. Section 1.8 is all about absolute value equations, and then we'll bring back the inequalities and how they apply to absolute values. So the one thing you probably remember from a previous class about absolute values is that when absolute values are involved, everything has to be positive. So when you solve equations using absolute values, there's something you have to be aware of. Let me use number 1 as an example of this. It says the absolute value of x minus 1 has to equal 7. Well, keep in mind, if this right here is going to equal 7, then there's two things that it could be. It could equal 7 because the absolute value of 7 is 7, but it could also be a negative 7 because the absolute value of a negative 7 is also positive 7. So my suggestion is that when you solve absolute value equations, for step number 1, get the absolute value by itself, which is already done here. Take the inside, and you're going to set up two different equations because there could be two answers here. The first one, I'm going to set equal to the 7 because that's what I need it to equal, but you could also set it equal to negative 7 because of the absolute value. Solving both of these, on the first one, if you add 1 to both sides, you get x equals 8. On the second one, if you add 1 to both sides, you get negative 6. And just for this first one, let me kind of double check it with you. Plug 8 back into the original problem. 8 minus 1 is 7. The absolute value of 7 is 7, so that's good. Plug in negative 6. Negative 6 minus 1 is negative 7, and the absolute value of negative 7 is positive 7. So that is why you have two solutions to this absolute value equation. All right, so now that we kind of went through the idea, let's work some other ones. What about number 2? The absolute value of 6x plus 7, then minus another 8, needs to equal 3. Well, step number 1 is you got to get the absolute value by itself. So I'm going to move that 8 over to the other side. So this would be the absolute value of 6x plus 7 needs to equal 11. And then just like number 1, I'm going to set up two different equations. I'm going to say that 6x plus 7 equals 11, and 6x plus 7 could also equal negative 11. On the first one, if I subtract 7 from both sides, this gives me 6x equals 4. If I divide both sides by 6, that is 4 over 6, which both of those share a 2 in common, so we get our first solution of being 2/3. On the second one, if I once again subtract by 7, negative 11 minus 7 is actually negative 18, and then dividing both sides by 6 gives you a nice answer of negative 3. So once again, there's an example of an absolute value equation that has two different solutions. All right, what about a couple of tricky problems? On number 3, it says the absolute value of 7x plus 3 needs to equal 0. Well, as you can see is that the absolute value is already by itself. Now, normally we would set up two equations here, but since 0 cannot be positive and negative, the only thing you have to do on this one is solve the initial. Excuse me. All right, because remember, there is no negative 0. So just solve this one equation. Subtract the 3 over. 7x equals negative 3. And then dividing by 7, you get a solution of x equals negative 3/7. And even better, if you're not careful, number 4 is a very commonly missed question. It says the absolute value of 4x minus 1 needs to equal a negative 5. But remember, absolute values can only equal positive numbers. So if you get an absolute value by itself and you get it equal to a negative number, there is no way to solve this. This has an answer of no solution. Now, I know you could set it up and probably solve for the answer, but that is not correct. So you need to pay attention. Absolute values cannot be negative numbers. So if that happens, you say the answer is no solution. All right, so let's move into the inequality part to wrap up this section. So let's combine what we did in the first part of this video with what the idea of absolute values tell us. So all these questions say, solve the following absolute value inequalities, express your answers in interval notation, and pay close attention to the inequality symbols. So on number 5, it says the absolute value of x minus 2 needs to be less than 3. So here's the good thing about less thans. So whenever you see a less than symbol, you can set this up as a compound inequality. And let me show you how to do that. So you see the less than. Take your absolute value part and write it down. The right-hand side doesn't change. It's still going to be less than 3, but you remember absolute values, you have to consider the negative case as well. So therefore, my lower bound starts off as negative 3. As we saw a little bit earlier today, get the x by itself. So I'm going to add 2 to everything. And you should end up with a negative 1 is less than x is less than 5. Well, negative 1 and 5 are your bounds. Neither one has an equal sign, so therefore they're going to have parentheses. So your final answer is negative 1 to 5. That's all it takes to do one like that. But where it can be tricky. So any positive number you see over here, you work it the same way. The only exception is what happens if it's 0, as you can see in number 6. It says the absolute value of 3x minus 7 is less than or equal to 0. But remember what this means. When something is less than 0, that means that it is a negative number. Absolute values cannot be negative, so there's the less than 0 part has no bearing on this. So I'm actually going to cross it out. But you still have the equal part. We do know that the absolute value of 3x minus 7 could equal 0. We saw this a few seconds ago. If an absolute value equals 0, there's only going to be one number solution. So I'm going to take the 3x minus 7 and just set that equal to 0, because there is no such thing as a negative 0 to check in this case. Add 7 to both sides, and you get 3x equals 7. Divide both sides by 3, and instead of having an interval notation, you have a singular number notation. So your final answer is x equals 7/3. Now, on your homework, if they do want you to put this into a interval notation, it's a little bit weird, so let me show you. If you just get a singular number, you're just going to have a 7/3. I know it's a little bit weird, but that's technically what the homework may ask you to do. So just be careful. The answer is just 7/3, but there is a strange notation with the little squiggle braces on your keyboard. That's how you denote one single number in your answer. All right, so let's flip-flop. What if we want to do greater than? This is the ones that take the most work, so let's talk about this. So when it's greater than, you're going to have to do an OR inequality, and those take the most work, remember from earlier. So let me show you an example. Number 7, the absolute value of x plus 4 needs to be greater than 5. So when I set this up and it says greater than, first thing I do is I write down exactly what you see without the absolute values. I'm going to put the OR for reference. You rewrite the x plus 4, And then not only must you flip the inequality, you must also flip the number as well. So then it becomes or x plus 4 could be less than a negative 5. As we saw earlier today, solve both of these separately. The first one, if you subtract 4, oops, that's not the right number, ignore that, x is greater than 1. Or if you subtract 4 from the other one, x is less than negative 9. Remember your line graph. Plot both of those numbers, negative 9 and 1, and I'll use a different color so you can see. The first one says x is greater than 1, so that's going to be this direction. Or x is less than negative 9, which is to the left. But with or statements, you cannot look for crossover. You have to write everything you've shaded. So all of this area and all of this area has to be included. So let's write those. The first interval starts at negative infinity and stops at negative 9, which gets a parentheses because of the non-equal sign. But you also have the second interval, which starts at 1 and goes to infinity. When your answer needs to include two intervals that don't touch each other, then you need to put a union symbol in between them. And that union symbol is on the palette in your homework. So your final answer for this one would be negative infinity to negative 9, union from 1 to infinity. All right, so let's work a second one. Since those are a little bit different, let's do a second one so you have it in your notes and you can follow along. Number 8, the absolute value of 7x minus 1 minus a 5 needs to be greater than or equal to 8. Well, first thing is I'm going to move that 5 over because you still have to get the absolute value by itself. So if I add the 5 to both sides, I can say that the absolute value of 7x minus 1 is greater than 13. Now to make sure I have enough room, I'm going to come over here to the right. Remember, it's greater than. It is the equal sign we'll deal with later. First thing you do is you write down exactly what you see, drop the absolute values off. So 7x minus 1 is greater than or equal to 13. Or you could say that 7x minus 1 and then flip-flop both things. Less than or equal to negative 13. Solve them both. The first one, if you add 1 to both sides, 7x is greater than or equal to 14. And if you divide by 7, x needs to be greater than or equal to 2. Or on the second one, if you add 1 to both sides, 7x is less than or equal to negative 12. And then dividing both sides by 7, x is less than or equal to negative 12 sevenths. Remember, the key word is or. So when you're drawing this number line, so negative 12 sevenths comes first, and then the 2. So according to this, x is greater than or equal to 2. So that's everything in this direction. X is less than or equal to negative 12 sevenths. So that is everything in this direction. All right. Since both of them have equal signs, we are going to use brackets on both of them. And you're going to end up using a union symbol just like number 7 because there is a jump in your answer. So your final answer should be negative infinity to negative 12 sevenths, union 2 to infinity. We use brackets this time on the two numbers because there was an equal sign in the original inequality. All right, and last but not least, probably the one problem to be careful about. Solve the following absolute value inequality. This one is a greater than, so once again, think about the or statements. Remember, greater than means or, but there may be a trick to this one. It says the absolute value of x plus 7 needs to be greater than 0. Now, here's your problem. If you try to work this the same way, let me show you what happens. Just like number 7 and number 8. If I say that x plus 7 is greater than 0, or I say x plus 7 also has to be less than, but there's no such thing as a negative 0. So actually your 0 stays there as well. So what does this say? When you solve both of these, the first one says that x must be greater than negative 7, but the second one also says is that x is greater than negative 7. Well, what does that look like on a number line? Since negative 7 is our only number, they want us to include everything greater than it, everything less than it, but did you notice what's not included? That's right. You cannot use the negative 7. So please do not use it. Negative 7 is not included. If there was an equal sign, it would be. But since negative 7 is not included, you have to write your answer to distinguish that. So I would start at negative infinity, and when you get to negative 7, you have to stop because you can't include it. Union, you have to jump to the other side and go from negative 7 to infinity. So just a little bit of a catch there. Be careful with the 0. It does work the same way, but the 0, since it's not negative, means almost every number works. The only number that doesn't work is the negative 7. All right, so that ends the video for sections 1.7 and 1.8. In the next video, we will finish up chapter 1 by doing section 1.9, and then we'll also start chapter 2 and do sections 2.1 and 2.2. See you in the next video.